Hello friends, welcome to Technocrats Expert Lecture Series. I am Mukherjee, Department of Mechanical Engineering, and today in this series we will discuss about an approach to efficient use of compressed air. In these sessions, we shall highlight on proper utilization of compressed air, about the challenges involved in this field, improving efficiency of productions, transmissions, distributions and utilizations of compressed air. We will also discuss the scope of energy conservations in compressed air system with the help of some real world case studies. So before we start, we should know about the compressed air. It is simply the compressed air is a gas or a combination of gases that has been put under greater pressure than the air in the general environment or atmosphere. Compressed air is a major prime mover for modern industry. Almost every plant has compressed air installations. The great advantage of compressed air is the high ratio of power to weight or power to volume. Compressed air is often referred to as the fourth utility after electricity, water and natural gas. Compressed air is one of the most expensive use of energy in a manufacturing unit. About 8 horsepower equivalent electricity is used to generate 1 horsepower of compressed air. Over the life of a compressor, energy cost is 5 to 10 times the compressor's purchase cost. So it can be well imagined that energy saving can rapidly recover the extra capital required to purchase an energy efficient air compressed motor. Now it is a simple diagram for production of compressed air. Compressor, there is a simple, it is simply take the air from the atmosphere and compress it with the help of energy input, and the compressed air is the output. The classifications of air compressor, broadly it is classified into two: reciprocating compressors and rotary compressor. In reciprocating compressors, it is again subdivided into two on the basis of number of stages for compression, that is single stage or multi-stage. Then number of sides of pistons in operations, that is single acting or double acting. Similarly, in the rotary compressor, again it may be subdivided into centrifugal compressors, screw compressors, etc. Now in this slide, we can see the PV diagram of the compressor. From the A to B is the compressions, the polytropic process. PV to the power n is the constant, and then B to C is the delivery or discharge. Then C to D is the expansion. Then again it is polytropic process, and D to A is the suctions. That is more clear PV diagrams with the coupled with the piston movement in the cylinder, and also shown the valve operations and what is going to affect on PV diagrams, that is also shown in this figure. Now, use of compressed air. Different industries have different uses. Air powered tools offered a number of advantages in many industrial operations, including the delivery of smooth power. Some manufacturing operations also use compressed air and gas for combustion or process operation, such as oxidations, fractionation, cryogenics, refrigeration, filtration, dehydration and aerations, etc. Now coming to the cost of compressed air. To produce the compressed air, what is the cost involved in it can be imagined that large sums are spent to generate this energy, which can be further compounded by higher operating and maintenance costs. To produce 100 cubic meter per hour of air at approximately 7 bar, 10 units of electricity are spent. So everything should be done to make sure that system operates at maximum efficiency and without any waste. Now the energy conservation aspect in compressed air systems. Energy conservation opportunities in air compressors and compressed air are tremendous. Many of the energy saving ideas can be adopted either at the design stage or during operations. The energy saving potential in compressed air systems vary from 20 to 30%. So there are two ways to conservation of energies in compressed air systems. Either in the design stage that will be carried out in the manufacturer end, but when the compressor is installed in the plant, it requires how to use, how efficiently we use, what type of decisions we are taking to use this compressed air. It is totally dependent on that. That we will go into discuss. Now the first and foremost thing, the sizing of compressor. So first we are going to install the compressor. The size, determination of size of the compressor, what size will take. Generally it is tendency for the future and scope or future development. Generally they take the higher size of compressor, but this has to be also a certain extent and certain limit. To minimize the unload power consumptions by correctly sizing the compressor, the total energy consumptions of the compressed air system depends on correct type and size of compressors. If the installed compressor capacity is much higher than the compressed air requirement of the plant, the compressor often falls in unloading mode. The unload power consumptions of the compressor is significant. In case of reciprocating compressors, the unload power consumption is the range of 15 to 20% of load power consumption, and for screw compressors, the unload power is still higher, which would be in the range of 30 to 35% of load power consumptions. During the unloading, the suction valve of compressor is closed. There is no air intake and no air delivery from the compressor. That is, there is no useful work done by the compressor. The power consumptions of the compressor is used only to overcome the internal frictional losses. Hence, energy saving can be achieved by minimizing the unload power consumptions. The unloading of the compressor can be minimized by correctly sizing of the compressor at the design stage itself. That is, excess cushions of capacity of the compressor has to be reduced. Maximum 10% excess capacity of the compressor is allowed. So what I did mention earlier also, that it is a tendency to take some higher size of compressor. It is a wrong concept actually. So the more the compressor will run on unloading conditions, that will be unnecessary power consumptions. So it is, our motto should be, the compressor always run in full load conditions to get the maximum efficiency. Now suction air intake in air compressor. After installation of compressor, as I did mention the compressor on the diagrams, that the compressor is sucked the air from the atmosphere and delivered in high pressures. So suction air quality and the type of the suction air, it depends on its efficiency. Like in the breath and the quality of the air, it's determined that how healthy we are. Similarly, the compressor efficiency and compressor performance is also dependent on the suction air. The compressor generates heat due to their continuous operations. This heat gets dissipated inside the compressor room, leading to hot air feed to the compressor intake. This results in lower volumetric efficiency and higher power consumptions. For an approximately 4 degrees centigrade rise in temperature, the power consumption increases by 1% for the same output. Hence, it is recommended to provide a separate suction duct from outside to the compressor directly. In the next slide, I am showing the diagrams. So the compressor, this is the compressor. When it is in operations, it dissipates heat. So by this, the room is getting heated, and the air, if the suction valve here and there is no duct, then the suction air, the high temperature suction air will be there, and which will reduce its volumetric efficiency, because the volumetric efficiency is the mass flow rate of the sucked air divided by the corresponding mass flow rate of swept volume. So if the temperature increases, obviously density will decrease, and less mass will intake, and consequently there will be less volumetric efficiency will get. So it is recommended that duct should be provided in the suction valve, and so that the cool and fresh air can be taken from the outside of the atmosphere. Then another important aspect is segregations of high pressure and low pressure compressed air systems. In the plant, different machineries are used, and the machines are required not only the same volume of air and same pressure, but compressor is one, and in the generation itself, a fixed pressure and fixed volume flow rate will be produced. As per our requirement, either we will install the regulator, or sometimes we use the unnecessary extra compressed air. And to eliminate it, the segregations of high pressure and low pressure compressed air system is very necessary. Higher the pressure, higher is the power consumption. In any plant, the compressor is selected for the higher pressure requirement, as I did mention, because from high pressure to low pressure it can be made with the pressure regulator, etc. But from low pressure productions, on the line itself we cannot increase the pressures. So that is why in generation itself the high pressure compressed air produced, and as per the requirement, if it is required in the low pressures, with the help of pressure regulator we reduce the pressures. But it is also care should be taken, and to see, or to closely it should be monitored, the decisions should be correct. As I did mention, the higher the pressure, higher is the power consumption. So in any plant, the compressor is selected for the high pressure requirement, though there is both higher and low pressure users. While calculating the average compressed air consumptions of the plant, the total requirement of low pressure, that is 2.5 to 3.5 bar, and high pressure above 3.5 bar compressed air has to be estimated. If any, say, lower pressure or higher pressure air constitutes more than 30% of the average compressed air consumptions, then the separate compressed air system has to be installed. So it has to be evaluated. If separately the lower pressure or higher pressure, it is 30% or more than 30% of the average consumptions, the average pressures, then a separate line has to be installed, or separate compressor has to be generation itself. Then another system, so very small things, but this can create the significant improvement. One of them is the use of loop piping systems. Generally, we generate the compressor, we are concentrated on the compressed air systems and the efficiency of the compressor. But the other aspect, when we are using the distribution parts, that is piping systems, these are also very important. So here, two types of piping systems we have is given: the straight piping and loop piping. Generally, the size of the plants are very large. So in the utility room, the compressor is there, and from compressor, the compressed air is accumulated in the receiver, and then the different users, and that is all starts from receiver to the end of the plant, and by this, to reaching at the last, so it is a significant pressures are dropped because of the frictions and other distribution losses. To overcome this, loop pipings are used. Loop piping means instead of straight piping, a loop has to be produced, and these are the compressed air users, different users, and one receiver is there and another receiver from the same compressor. So after filling up this receiver, and again the receiver number 2 will also filled up with this required pressure. So when the pressure get dropped up to this point, again from this receiver it will compensate. So this is a piping systems which can used for compressed air systems to get the higher efficiency. So this is more clear pictures actually, shop floor, how the piping system done. This is the straight piping system from compressor to air. It should be avoided. Instead of this loop system has to be installed. Then another important part is distribution of branch connections. Distribution of branch connections should be taken from the top of the main manifold to the reduce moisture entrainment in the air. In compressed air systems, it is invariably that moisture contents are there, which is avoided. So in the main manifold, when the compressed air, the main compressed air is coming from the compressor room, and when we are using through the branch, instead of taking this branch from the bottom of the manifold, it should be top of the manifold. So whatever the water contaminants and moisture is, etc., it will get settled in the main manifold, and branch pipe, the dry air will come. So this is also a small decisions or small corrective actions in piping when we are doing the piping, but create a significant improvement and significant change. Other useful measures for compressed air distributions. One of them is the pipework should be fall in the directions of flow, and the gradient can be kept at approximately 1 in 100. Instead of straight piping, the pipe should be in a slope, so that the drain trappers will easily trap the moistures. Actually, moisture trapper should be installed every 40 to 30 meters of the pipeline, and the main line can be installed at every 30-40 meter of effective water removal. Install the pressure gauges in various sections of the entire distribution system for monitoring the pressure in different sections of the network. The number of joints and bends in the distribution network should be as minimum as possible. So these things can be well visualized in the next slide in this picture. As I did mention, that pipeline should be in the slope. The slope is in the gradient of 1 in every 100. So this is the slope, and as minimum as possible is the pipe fittings, bend, union, etc. So that if the length of the pipe is also high, then instead of making joints, the welding joints can be made, and so that a single seamless pipe and length can be installed instead of unnecessary bends on which will give the frictional losses and etc. and ultimately affect the efficiency of the compressors. These are the moisture trapper and drain valve are there, and as I did mention, after a certain interval the drain valves are provided. So these are the things. Now we'll have some case studies. It is picked up from the real world, some manufacturing units, and by some innovative ideas and some decisions making, small things have given a significant saving or significant conservations of energy. So case study number 1, optimally utilize the compressor depending upon the requirement. The background was, in a packaging manufacturing unit, 2 screw compressors, each of 125 cf in capacity, were in continuous operations. Majority of compressed air users are pneumatic controls, pneumatic clutches, pneumatic valves and actuators. In addition, compressed air is also utilized over there to positioning the trimming cutter of in a compound die. So there was two compressor as I would mention, 125 CFM, but some measures has been taken. What the measures were? First one, a reciprocating compressor of capacity 25 CFM was installed to meet the compressed air requirements for pneumatic clutches where pressure is important than the volume. As I did mention earlier also, the air pressure is not same in all and each and every machines. As here, the clutches for pneumatic clutches, the pressure is important, but volume of air is less and there is no continuous flow. Only when engaging or disengaging the clutch we require the pneumatic pressures. So small volume of air but high pressure is required. But high pressures we cannot, in the middle of the pipeline we cannot increase it, because at the source the compressor should be of the higher pressure compressor. So it requires the much higher power or energy requirements. But requirement is less. So what was the decision? Decision was a small size of compressor. Instead of 125 CFM screw compressor, only 25 CFM reciprocating compressor installed to meet the compressed air requirement for pneumatic clutches. But the pressure is important than the volume. The second, one screw compressor of 125 CFM was dedicated for other user like pneumatic control, positioning the trimming cutter and shifting of light materials etc. where continuous air supply was required but at low pressure. So it is the just reverse of the previous one. Here volume is important but pressure is less. Number 3, over and above, the control valve operated by a cam and follower systems was installed in order to provide air supply to the dies only at the point of requirements. So another small attachment was made, one opening and closing was made for the dies when the high pressure is required, but only on that time, instead of giving the continuous pressures, it will give only air when as and when it is required by the use of the cam and follower, and then cam and follower will operate the valve, and the valve as and when it is required it will give the compressed air to the die. So these were the measures were taken. So that, as I been mentioned, the separate compressors were made, compressor 1 and compressor 2. This was the initially. Then this was the decision. An auxiliary compressor, this auxiliary compressor, that's 25 CFM in this case, was installed for the operating the pneumatic clutches, and these were the main compressors. So this was the 125, 125, 2 in addition and all the auxiliary compressor. But result was that this auxiliary compressor of the less power consumption compressor is replaced the 125 CFM big compressors, right? So this was the improvement. So what was the benefit? Benefit was 125 CFM compressor were replaced by a 25 CFM reciprocating compressor with on-off switch. The unload power consumptions of the screw compressor was totally eliminated. Consequently, there is substantial energy saving. And the techno-economical analysis or financial analysis was that on that during those days, the annual energy saving achieved was 6 lakhs, and this required an investment of only 80,000, which was paid back in 2 months only. So this was the small decisions, a small investment, but a substantial running cost was eliminated. So it is a great success story. Similarly, case study number 2, another case study. It is the use of Venturi effect to fulfill the requirement of compressed air and vacuum generation simultaneously. Let us see what was the background. In a machine made for embossing of a pilfer-proof caps, there were requirement of continuous supply of compressed air and vacuum generation simultaneously. Supply of compressed air was given from main manifold and a vacuum pump of 5 horsepower capacity was installed to create the vacuum. So there are two requirements. One is the compressed air to run the tools or to operate the tools, compressed high pressure air, and negative pressure was there to create the vacuum, and this vacuum was for a holding tools. Actually, the pilfer proof caps is a very delicate item. This is the bottle crowner actually, bottle cover. So the aluminum caps are there, pilfer proof caps. So it cannot be held in a traditional vice or traditional holding tools. So it is required just create the vacuum, so hold the tools for a while so that embossing can be made, and that embossing tools is required the compressed. So simultaneous use of the positive high pressures and negative high pressures. So both are created by different machines. So old method was the method piece is fastened, and workpiece is fastened by vacuum, which is produced by separate vacuum pump, and pneumatic embossing tool is operated by compressed air, and same is generated by screw compressor situated at central utility. So this was the old method. So a vacuum pump was there. This is the vacuum pump run by a motor. The motor is taking energy and energy consumption is there, and by creating the vacuum, and suction stuffs are there, and the suction stuffs, with this help of this, the caps were held. This was the old method. Then modified method. In modified method, instead of this vacuum pump, a vacuum generator. We'll discuss later that what is the vacuum generator and how it is work. So, but the layout I am showing that instead of vacuum pump, a vacuum generator is there, and the vacuum generator is there where the compressed air is used to create the vacuum. Right? This is a modified method. Separate generation of vacuum and compressed air are replaced by using a vacuum generator. And this is the workpiece, and this is the embossing tool, which is using the compressed air. So compressors, from compressor it is getting the compressed air, and with the help of Venturi effects, it is getting some vacuums, and with these vacuums the workpiece are getting fixed on the vacuum holder, and the exhaust compressed air which is going to waste is using this embossing tools. So more clearly you can see the vacuum generations, how the Venturi effect and Venturi can operate. Compressed air enters through inlet A. The inlet A, from here the compressed air is entering, and in the point B causes the air stream to increase the velocity. Here in the point B, the throat is there, like simple Venturi meters, we can compare with that. It is a Venturi effect. And in the point C, there is a generation of vacuum. And in the point D, the compressed air is going outside with the muffler. This is more clear. The Venturi working on the vacuum generator. This is a Venturi effect. The air inlet, and this is the throat, and the air is discharged. Through here, it is getting the higher velocity and discharge in the atmosphere. But in our case, we are using this discharge here for running the tools and the vacuum. Vacuum pump and vacuum generator. This photographs you can well imagine. This is the vacuum pump, was 5 horsepower motor, and this vacuum pump was operated with this motor and creating the vacuum, and we are using the holding tools. It is replaced by a simple pipe fittings, you can say. There is no extra energy is required, only one side is the compressed air, it is connected with the compressed air systems, and another is with the outlet, and here the vacuum is created. But this is the simple, how simple the vacuum pump total this complex systems to a simple systems, how it is switched over. Then the flow curve of the pump and Venturi that have the similar performance with the help of this curve fittings. It has been shown that the use of pump and the Venturi almost the same, so it is coincide. The airflow and venturi and the vacuums, it is made by the pump and the venturi. The blue color is for the venturi and red color for the pump. So almost it is the same performance and similar performance without using any extra power or extra energy for running the compressed air. So what was the energy saving? Vacuum pump is replaced by venturi vacuum generator, which served both the purpose of air supply and vacuum generations. There was a significant reductions in power consumptions and hence the cost of the compressed air. This is because of use of exhaust air to run the embossing tube, which otherwise going to loss. Moreover, use of vacuum generators helps to maintain workplace clean, noise-free and less pollution. The energy saving was found to be in the tune of 15%. And additional advantage, in addition of this, what were the other advantages got? It is, you can say, the consequence of the use of the vacuum generator, of course, in the positive way. The first is the fast cycling. Since there are no moving parts and the time to establish vacuum is low, venturis are suitable for fast cyclic applications. Then temperature. Venturis can operate over a wide range of temperature, especially at high temperature applications. Then you can also use in the corrosive environment. Since venturis can be made out of a wide range of materials and there are no moving parts, they can work in corrosive environment also. Noise levels. The only noise generated by venturis is due to the airflow and can be minimized by using noise reducing muffler. The contaminations. Venturis, especially the single stage venturis, are quite insensitive to contaminations. Even if particles are entered into the device, they can be cleaned without any complexity. Then the maintenance. Since there is no moving parts associated with these venturis, they are practically maintenance free. Then easy to install. Venturis are quite compact. They can mount it very close to the workstations. This makes them as a part of the end of arm tooling, which minimize the length of vacuum line. So this is a small device. Another different power supply is not required, a small pipe fittings you can say. So as and when it is required directly, it can be used at the place of working. So lengthy pipeline can be eliminated, which further can be friction losses can be compounded. So that can be avoided. Then lower cost, due to their simplicity, the venturis are very low cost components as compared to the vacuum pump. So these are the additional advantage. At last but not the least, energy utilizations plays a vital role in manufacturing unit. It also seeks to put forward the methods and means for optimum utilizations of energy and design innovations, which proved to be very promising. A finite planet cannot sustain with infinite use of goods and services. The slogan for current era is reduce, reuse and recycle. So in these sessions, we try to understand the implications of the energy savings and energy utilizations on the compressed air. The compressed air, it is an essential part of the modern industry. We cannot avoid it. The utility it is considered as the fourth utility that also we have discussed. So we cannot avoid the use of the compressed air. We have to use the compressed air, but by smart using, which we have discussed in these sessions, definitely can create the significant change towards the improvement and efficient running of the compressors, and energy saving can be achieved. Thank you very much.